In today's class, we're going to expand upon the ideas that we have covered with respect to single electrons on hydrogen atoms and the calculation of electronic states for more than one electron on an atom, plus the concept of identical particles and the fact that we can't put two fermions into the same space and spin state, to understand some of the behaviors of atoms in the periodic table, multi-electron atoms. Our primary source for this discussion is the required textbook by Crane, Modern Physics by Crane, the first few segments of Chapter 8. And there's some additional discussion on the structure of atoms in Townsend, 7.03, chapter 7.3. And surprisingly, there's some pretty good material with respect to understanding this in the freshman textbook, Young and Friedman University Physics, chapter 41. Our motivation and background for this material is that we want to understand the systematics of the atomic properties and the periodic table. And those properties include how orbitals are filled, what the approximate energy levels for the orbitals might be, and the behavior of the outermost electrons, those in the highest energy orbitals. That would be related to ionization energies and electron affinity. So we're finally getting to the point where we're talking about chemistry a little bit. And then the other property that can be relatively easily understood based upon what we have learned so far are the X-ray absorption due to X-rays or electromagnetic radiation that excites an electron out of a core level that is a 1s state or a 2 state, n equals 2 state. Normally, as soon as we get up to reasonable sort of intermediate atomic numbers, let's say 10 or so, then we're into the X-ray regime for those electromagnetic radiations. And also characteristic radiation that is emitted due to transitions between states that are near the core of the atom. So as a reminder of what we have previously learned and how we're going to extend things, we know so far that if we look at electrons on a hydrogen atom or electrons in a spherical potential, in either case, then we have a principal quantum number which is associated with the number of nodes in the radial wave function portion of the wave function. We have an orbital quantum number, which is related to the number of nodes in the angular portion of the electron state, and is related to the orbital angular momentum. We have the orbital magnetic quantum number, which is related to the magnetic moment of the atom in a magnetic field and corresponds to the projection of the angular momentum onto the z-axis. And then we have the spin magnetic quantum number. So we have 4 quantum numbers. And we previously learned that the Pauli exclusion principle states that no 2 electrons can occupy the same quantum mechanical state in a given system. That state includes the spin, so we can have 2 electrons in any given space state characterized by n, l, and m sub l. So here's a listing of some of the sets of quantum numbers that can be allowed for electron states in an atom. The actual energies aren't going to necessarily correspond to what we learned for hydrogen, but the quantum numbers are still useful quantum numbers. In particular, if the potential is a spherically symmetric potential, then the angular momentum and angular momentum projection quantum numbers will still be useful, good quantum numbers that describe eigenstates of the system. The details of the radial states may depend upon what other electrons there are in the system. So when we're characterizing states, we can always look at a table like this and characterize principal quantum number, angular momentum. There's one other thing that I want to mention here, which is that there is a notation. So we talked about spectroscopic notation, but there's an additional notation that is related to what people observed in X-ray spectroscopy, which relates to once again, the principal quantum number. And this is called the shell quantum numbers. And so a principal quantum number of 1 corresponds to what's called the K shell for electrons. Principal quantum number of 2 corresponds to the L shell, 3 M shell, 4 N, 5 O, KLMNO. Okay? So I mentioned here again our shell terminology, and here's a picture somewhat of the listing that I gave you previously on the table on the previous page. 1s state, 2 states S and P, the 3 states SP, and then D is here, and we'll understand a little bit more about why the D state ended up in this range here, 4 states, and so on. We'll find as we proceed that if we want to estimate the energy level for an electron in a system, that it is useful for us to just use the old Rydberg series type idea, but where we've modified the effective charge of the nucleus in some odd way. So here's our Rydberg 13.6 electron volts, our principal quantum number here, and then we have some effective charge that the electron in a given level sees. And that's a big part of what we're going to be talking about in the next few slides. In the next several slides, I actually mean. So if we want to actually compute wave functions and energies, we would use the Hartree-Fock approximation, for example, the approach calculation, where we calculate the energy of an electron by calculating the potential due to all of the other electrons, find its wave function and energy, and then take that wave function and use it to calculate the states of other electrons. It's a very computationally intensive process. But in that concept, there is one simplification that we're making, which is that every electron looks at a spherically symmetric distribution. We know that's not quite right because we know that if 2 electrons are in an antisymmetric state, then on the average they'll be further apart. So it's not strictly a spherical distribution, but those corrections are small. I showed you this in the last class, and here's just an example of the concept of screening. If I'm interested in calculating the effective energy of an electron in the 2s state, so L equals 0, N equals 2, L equals 0 state of a helium atom, then a reasonable approximation is to calculate the first electron on the system, which would be in an N equals 1, L equals 0 state, calculate the energy of the first electron and the wave function for the first electron, then bring the second electron in, which now, if it's out here, sees a nuclear charge of 1 because the first electron sits inside of this radius, and therefore by Gauss's law, the field out in this region looks as though there's only a charge of 2 minus 1 inside of it. And so out here, the wave function could be calculated based upon an effective nuclear charge of 1. And then as we move further in, this wave function here begins to overlap into that one, and the effective nuclear charge changes. However, there's always the idea that the inner electron screens, by Gauss's law, screens the outer electron from the full nuclear charge. And we need to make an adjustment to that effective charge that this electron sees. So that is the concept of screening. Electron probability inside of an orbital screens that orbital from the full nuclear charge and changes the wave function as a result. So we really want to do this correctly. What we would do, again, is use an iterative method where we calculate one electron, put the next electron in, calculate that electron, take the wave function from that electron, plug it back in, and recalculate the first electron again. Keep repeating until things settle down to our satisfaction. And then if we have more electrons, add the next electron and recompute everything again. So just to repeat the idea of screening, here's an example of a lithium atom, for example, has 3 electrons. I'll talk in more detail about that in a moment. And electrons that are in the n equals 2 shell out here, in this state here, on the average spend their time outside of the n equals 1 orbital or shell. And there are 2 electrons in the n equals 1 orbital or shell. The nucleus is 3 plus 3, and therefore the electron that's in this outermost orbital only sees 3 minus 2 for the effective charge, approximately. Again, the wave function does penetrate within this orbital, but as an approximation to what's going on, we say that this orbital here, electrons in the 1s orbital, sit within the 2s orbital, and as a result, screen the electron in the 2s orbital from the full nuclear charge. So to extend that just a little bit, an atom of atomic number Z has nuclear charge of Z times the electron charge, and then it has Z electrons of charge minus E each. Electrons in the outer shell see a nuclear charge of Z effective, where Z is less than Z effective is less than the actual nuclear charge, because that charge is screened by the electrons of the inner shells. So we can calculate the energy of an outer electron by somehow deciding what effective charge to use. And we do the calculation using a simple hydrogenic orbital approximation, and then it's just a question of what effective nuclear charge we use. For an electron in a given orbital, how much of the nuclear charge is screened by the other electrons in the system. So let's go through atoms, at least a few atoms in the periodic table, and discuss from what we know what we would expect for the behavior of these atoms. So we've talked a little bit about lithium, now we'll be explicit about it. So the first thing is that we could ask, based upon the principles that we've learned, whether or not it's reasonable for us to put all 3 electrons in the 1s ground state. Okay. Remember that electrons can only have spin up or spin down. And so if I put all 3 electrons in the 1s ground state, then it's certain that 2 of the electrons in this ground state will have the same spin. And if that's the case, if they're in the same state, then it will turn out that when we exchange them, we get the same state back again. And so the state that we try to make ends up having 0 amplitude. So we can't put all 3 in the 1s orbital. You already knew that from your high school chemistry course, but the more fundamental argument here has to do with the symmetry under exchange of electrons in states. So now we put the third electron into the n equals 2 state, and we might ask, all right, is there a preferred n equals 2 state for this electron to go into? From our strict hydrogenic calculations, the n equals 2, L equals 0 state has the same energy as the n equals 2, L equals 1 state. And so there wouldn't be a preferred state for the electron to go into. However, it turns out that there is, because the actual wave function of the 2, 0 state has a different shape, a different radial shape than the 2, 1 state. The n equals 2, L equals 0 state has more amplitude inside of the n equals 1 state, the 1s state, and therefore it experiences a little bit more of the nuclear charge, and therefore is more tightly bound than the L equals 1 state. So we expect then that the configuration would be 1s squared, 2 electrons in the 1s state, and 1 electron in the 2s state. We can say a little bit more. The 1s electrons would partially screen each other. So for one of the 1s electrons, the other electron spends about half its time inside of its orbital. And so it would partially screen the second electron by about half an electron charge. So for these inner electrons, the effective nuclear charge that they see, instead of 3, is about 2.5. And that's very rough, but it's not unreasonable to guess that. And the 2s electron then would actually be mostly screened by the 1s electrons, so the effective nuclear charge would be about 1. And the energy of the 2s electron would be pretty close to the 2s level of hydrogen then. So the first ionization energy for helium would be around a quarter of that we would see for hydrogen, maybe 3 electron volts. Not that far off from what we actually see for lithium. So I want to look at some patterns that we're going to observe for heavier atoms. Remember, what we said was that the innermost 1s electrons are pretty much going to see the full nuclear charge, whatever it might be, Z, minus about a half or so. When we get up to much heavier atoms, it's going to turn out that the screening due to all of the outer electrons adds up to about half an electron as well. So this inner electron here sees a nuclear charge about Z minus 1. And so if we talk about the binding energy for this state, it's going to be the binding energy of the hydrogenic state, where the effective charge is Z minus 1, approximately. So if we look at the absorption, optical absorption spectrum for atoms, as we increase the, we're going to go this way. As we increase the energy of the exciting radiation in this system, we would, if we had states up here that were filled, we would excite those states and we'd see an absorption edge due to the energy difference between the state and releasing the electron into the vacuum, so the electron can travel here. And each time we cross through one of these energy levels, we're going to see a jump in the absorption spectrum. So energy is increasing to the left here. We start at low energy, and we don't have we have absorption due to these states up here, and then we get to a particular state. These are our L orbital states, and at this energy, when we get to an energy here, let's choose, this energy here, then we can remove an electron from the system, and we see a jump in the absorption coefficient due to that cross-section for that removal. And the highest energy state to remove an electron from the system is the one in which we remove the K electron, or the 1s electron, from the 1s orbital to the vacuum. And there's the absorption edge for that one. The details of the magnitude of the absorption coefficient depend upon diameters of orbitals and matrix elements, but there is an absorption there due to the K edge, right? So that's X-ray absorption. What is seen experimentally, this is the example for platinum, by the way, experimentally, is that K edge, the position of the K edge, varies, for the moment, I'm going to say non-linearly with the atomic number. And that is as it should be. You might expect that it's going to vary as atomic number squared, right? So let's take a look at that. There's another type of spectroscopy that we can do here. What we were doing was shooting X-rays into a system and looking at the absorption coefficient for the X-rays. Here, what we do is bombard atoms with high energy electrons or X-rays, and then we look at the X-rays that are emitted from the system. This is actually the basis for fixed anode X-ray emission system. We get a combination of things in the spectrum. There's a continuous spectrum that is the result of what's called breaking or bremsstrahlung radiation due to the electron accelerating or decelerating in the system. But then, in addition, there are strong emission lines that are called the characteristic X-ray emission lines. These characteristic lines are actually used to determine what kinds of atoms there are in a system. So this is one of the most important tools that chemists and earth scientists have for observing what is actually in the system that they're looking at. These are the characteristic lines for molybdenum. The previous page was platinum. So what are we actually looking at here? Something comes in, either an accelerated electron or a high energy electron or an X-ray, and excites an electron out of the 1s orbital. So that's an electron being excited out. And that leaves an empty state here and a bunch of states up here that actually have electrons in them. And what happens then is that an electron, let's say in the 2s or 2p or 3s or 3p orbital, it's actually going to be p orbitals, decay then are captured into the 1s orbital. So I should actually change this here. The excitation is from 2p to 1s and 3p to 1s, right? They have to be allowed transitions. And when that happens, X-rays, light, are emitted, and that's what the characteristic lines are. So we end up looking at the differences in energy between this state and that state and this state and that state. The characteristic X-ray emission lines. It was observed in the early 1900s by Moseley that the wavelength of those emission lines obeyed a relatively simple relationship. That is, that the 1 over the wavelength, or the energy of the X-ray that is being emitted, correlated as the square of the atomic number. And then the intercept here, turns out, corresponds to approximately 1. That is, that the energy of emission is related to z minus 1 squared times 1 over n1 squared minus 1 over n2 squared. And again, this kind of relationship can be used to establish by measuring the characteristic lines that are emitted by a system what atoms we had in a particular system. To continue with the periodic table now, to talk about some of the other features. So we've talked now pretty much about the full periodic table, and that previous graph led mostly to propose the periodic table. But we could talk about other features of atoms in the periodic table. And the next atom we could talk about here is beryllium. So seems reasonable here to put 2 electrons in the 1s state and 2 in the 2s orbitals, right? Again, they prefer to go into the 2s orbitals because those orbitals penetrate a little bit better into the core inside of the 1s orbitals, and as a result lead to tighter bonding for the 2s orbitals. And the energy level for those 1s electrons could be estimated by taking an effective nuclear charge of about 3.5. They screen one another by about 1/2 an electron charge. And we guess then that the binding energy would be about 140 electron volts. It's actually somewhat smaller, 112. And the difference is that I've actually got these other 2s orbitals here, and they do have some penetration into the core, and they do screen the initial electrons a little bit from one another, and as a result, the binding energy is a little bit less due to that additional screening. The 2s electrons, we can make some, the 1s electrons we've got a guess. For the 2s electrons, we can look at those and say that the 1s electrons, fully screen them from the nuclear core, so it would be z minus 4 minus 2 for the 1s electrons on the inside, and then each of the 2s electrons screens the other one by about 1/2 a charge, and so the effective nuclear charge for them is 1.5, and that's what we would stick in to calculate the ionization energy. And from this, by the way, we calculate that the ionization energy would be about 1.5 times that of lithium. Actually 1.5 squared, so about twice that of lithium. The total electron spin would be 0 because the 2 electrons in the 1s orbital are spin up, spin down, and the 2 electrons in the 2s orbital are spin up, spin down. Z equals 5. Don't worry, we're not going to do the entire periodic table. We'll do boron, and then we'll skip up to a slightly heavier atom, and then generalize from there. But the point is that an argument like this can be made for every atom in the series, and we can infer the properties of each atom in the periodic table by thinking about what are the core electrons doing, and that gives us some idea of the X-ray characteristic lines, and what are the outermost valence electrons doing, how are they responding, how are they screened, and what are their energies, and that gives us an idea of the electron affinity or ionization energy, and some of the energetics and symmetry, so we can decide what kind of binding is going to occur when we make molecules. So we learn about chemistry. The 1s electrons now have an effective Z of about 4.5 or a little bit less. Start with 5, and they screen one another, and then the outer electrons screen a little bit too, so a little less than 4.5, and we guess a binding energy of about 200 electron volts from that. So that would be the characteristic lines, the characteristic absorption. The 5th electron is going to go into the 2p orbital, And the 2p orbital doesn't penetrate into the core as much, and therefore it's only going to be partially screened by the 2s electrons. It will be screened by the 2s electrons, and it is screened by the 1s electrons. So this outermost electron sees a nuclear charge of about 1, but maybe a little bit more because it does have some portion of its wave function that penetrates into the core. The electron spin would be a half, and remember the 1s and 2s electron spins cancel, so the total spin of the system would be 1/2, and the total orbital angular momentum for the system would be 1, because the s orbitals have no angular momentum. A little heavier now. Sodium, Z equals 11. 1s electrons would be bound with a Z effective of about 10 now. Remember, we would have said 10.5, but we've got a lot of outer electrons now that can penetrate in, and they're going to reduce the effective charge. So we'll put 10 in there. And so the binding energy would be around, we would guess, 1360 electron volts. Experiment says 1071. So we're in the ballpark, right? The 1s, the 2s, and the 2p orbitals are filled. Remember, the p orbitals can hold 6 electrons. So 2 and 2 is 4, and 6 is 10 electrons. And then there are 11 electrons, so there's one more. That outermost electron goes into the 3s orbital. And the n equals 1 and 2 electrons screen that 3s orbital by quite a bit. So again, the external, the 3s electron sees a charge, an effective nuclear charge, of only about 1, because all those electrons are sitting inside of it. And so we would make a guess as to what the effective Z is. I would guess 1, but when we actually work this out, it turns out that the effective Z squared, I think, is 1.7. So we expect the binding energy of the 1s electrons to increase as Z minus 1 squared. That's called Moseley's law, because the nuclear charge goes up. And we expect the binding energy of the outermost electrons to increase within a row of the periodic table, because if we're within the row, as we add nuclear charge, then the outermost electrons are actually in the same orbital as the previous electrons, and as a result, they do screen one another to a certain extent. All of the outer electrons, the valence electrons, are screened by the inner electrons, but they also screen one another. And so as we continue to fill the outermost shell, we get partial screening by the valence electrons, the outermost electrons. So it's not complete. And as a result, we build up the binding energy for those outer electrons. And the inner electrons, as we increase Z, get more and more tightly bound. As a result of this screening effect, the noble gases should have the highest binding energy, and alkali metals, where you've just got one electron sitting outside of a closed set of closed shells, should have the lowest binding energy. And if we look at the systematics experimentally, we'll find that to be true. I'll show you the slide that shows the ionization energy in a moment. I'm going to go outside of all the textbooks and pick up a useful reference here. Again, this is something that chemists primarily use, but it's useful for us because it sort of takes everything that I've said about screening and puts it into a set of rules that can be applied to do a calculation. These rules are called Slater's rules. I picked them up from here. Right? They allow us to estimate the energy and wave function, the energy, for an electron in consideration of the effective screening. And so here they are. Slater says, go ahead and write out the electron configuration starting in the following form. 1s electrons form a shell. 2s and 2p form a shell together. 3s and 3p form a shell together, and 3d sits somewhat outside of the 3s and 3p orbitals. 4s, 4p, 4d, 4f, and so on. Okay? So now we're going to worry about a particular atom and an electron within a particular atom. So let's say we've got a heavy atom that fills up all the way to 5, but we're interested in the energy of the 3s electron. Right? We identify that electron that we're interested in, and then we ignore the effect to first order of all of the electrons. So if we were interested in 3s, we ignore the effect of all the electrons out here. They sit outside of this shell. They don't shield the electrons in the lower groups. And then Slater's rules allows us to figure out what the effective nuclear charge is for that electron. Electrons within the same group shield 0.35. Remember, I made the argument that an electron in the same group would shield about half an electron charge, but a better estimation is about 0.35, except the 1s, which shields 0.3. Electrons within the n-1 group, so we're interested in 3s, electrons within the 2 group, all right, shield 0.85, and electrons further in than that shield 1, each one of the electrons. So if we were looking at the 3s electron, we'd take z minus, now I've got 8 of these, okay? So 8 times 0.85 subtracted from z, and 2 times 1 subtracted from z. So we would subtract that much nuclear charge. Okay? And then follow the rules here. Electrons within the same group shield 0.35. We weren't talking about the D or F electrons, so we didn't worry about that. It was just this one here. So we would worry, in terms of shielding, about the electrons in shells inside of the 3s and the 3p electrons themselves, which would shield by about 0.35 each for each electron. That table, that set of rules that I just showed you, actually does a pretty good job, and I'll have you compute this, of predicting what the ionization energy for the outermost electrons in as a function of atomic number are. And the pattern that we talked about is held. Lithium, in this row of the periodic table, lithium has the most easily removed electron because it sits outside the charge of the nucleus. It sits outside of the 1s orbital, and as a result, the electron here is pretty well screened from the nucleus. And then as we proceed, we see that the binding energy pretty muchly increases with little dips when I have filled a level here, and now I'm looking at the next set. Then I put 3 electrons into the p orbitals, and then when I have to change the symmetry of the state, because now I'm putting 2 electrons with the same spin, so I have to go into a new space state and reconstruct my symmetry. When I do that, then there's going to be a dip in the binding energy. And so we can actually get some idea about this pattern here from our arguments about symmetry and our arguments about the hydrogenic states and the effective nuclear charge. And this, understanding how this behaves, allows us to predict, in many cases, whether a chemical reaction is going to occur or not.